There it is. We'll go ahead and get started. So if you haven't already, go to that QR code. It is, oh, am I sharing my screen still? I can't tell because it's full screen. It says I am, but I don't see like the green bar around it. They said I am. Okay.
You can see
the OneNote QR code. Cool. So I don't know. Why is that thing over here? Okay. All right. So yeah, if you haven't already, go to that link. That is like how ACM tracks attendance for these things, and you'll get like points for it. So you should definitely do that. So I want to go over a couple things today, just like some housekeeping stuff before we get into the content. So a lot more people filled out the like application survey, which was great. I think over like 120 people filled it in, which is awesome. I got a lot of feedback on like what people are interested, what they want to learn. And I just want to touch on some of that. So a lot of people were looking to learn very like valuable things that they're looking for specific things that they can apply to whatever field they're interested in. Which I understand why they put that, because this is called like CS Essentials, and the whole marketing is that like I'll teach you things that you don't learn in your classes. So that makes sense as a request. But a lot of the like specific ones, like there was a lot of like stuff about web development, specific things within that. We're not going to cover any of that. The point of this is to give you stuff that applies to every field. Just I want to make each lecture like as useful to everyone as possible. So I'm not going to go like super in depth on any topic. So yeah, just like, sorry if that's what you were looking for, but I guarantee you that even if you're not going to get what you were looking for, you will still find some useful stuff here. Okay, so with that, we will get into today. So what we're talking about is, I've just called it numbers and math, which is a pretty boring name and a very general name. But we're going to be talking specifically about like binary and how the computer stores numbers in various formats in binary, and how you can identify those formats and read them and do some basic operations on them. And this is like right off the bat, sort of diving into the deep end of stuff that I was talking about last time, which is like, it doesn't really help you in one area in particular, but I can promise you that knowing this stuff, like it does help in weird ways. And in addition to that, a lot of this, maybe not all of it, I think some of it though, you will need to know for computer architecture if you haven't taken that. If you have taken it already, then hopefully this won't be too much a review and you will learn some new stuff. But okay, so let's start off here. Let me actually delete. No, I'll leave that up there. Okay, so there are two types of numbers. I think everyone knows this. We have ints and floats. So ints are basically, that's my best approximation of the like integer symbol, and then floats are just real values. Integers are whole numbers, but they can also be negative, and floats are just, I mean, theoretically, they're like any real number, but as we'll see, that's far, far, far from true. So we're going to talk about both of these today. I think these are actually like the only two types. There are different variations of both of these, but I don't think there are any other like fundamental data types that computers store. So we'll start with ints because those are easiest. You've probably seen that before. And then we'll get into floats, which are a bit more interesting and have some pretty cool math associated with them. Okay, so within ints, there are two types. There are signed and unsigned. And signed values, we'll see why it's called signed and unsigned in a minute. But signed, just know that they can be negative, and unsigned can't. So they are exclusively greater than or equal to 0. And this is maybe a weird concept to some of you if you're used to just languages like Java or JavaScript or Python. That I think all of the like integer types there are signed, except for maybe like char in Java, which I think is unsigned. But in either case, you don't have control over the signedness of an integer. But one of the cool things about C and C++, and again, this is just like why it's such a useful language to demonstrate this stuff, is that you can actually directly control for independent variables, whether they are signed or unsigned. And there are two keywords for that. They are signed and unsigned. But the signed is implicit. So basically what that means is if I have int x equals 5, that is the same thing as signed int x equals 5. There's like just no reason to write signed x equals 5. I honestly, I don't even know why that keyword exists. Maybe just it makes it a bit more clear what's happening. But unless you specify that it is unsigned, it's a signed value, which means that it can hold negative numbers. So let's actually look at unsigned values first, because those are a bit simpler. I got a message from Zoom saying I've been signed out. I think it's still working. Hopefully. But yeah, so let's look at unsigned values. And just for completeness, I'll show you how you would write that. So you would write like unsigned int x equals, well, you could do -1 and that would have some weird results because technically that's not a valid unsigned integer, but we'll look at that later. So this is how you would just say my int x here is 32 bits and it can only store positive values. And these are probably just like what you're used to thinking about, unsigned values. Like I'm sure in one of the intro CS classes, 1200 or something, they just talked about like how to count in binary, how to convert to hex and maybe octal and stuff. And when you were doing like basic addition in binary, this is probably what you saw, unsigned integers. So just as an example here for this integer 5, in binary, this would be, you usually precede binary values with 0b, 0, 1, 0, 1. So that is 1 times 1, 0 times 2, 1 times 4, and then 0 times everything after that. So 4 plus 1 is 5. So let's just look at a basic example of unsigned integer addition. I think I'll just take 5 because it's super easy. So we'll do 5 plus 9. So we have 0, 1, 0, 1, and then 9 is 0, 1, oops, 1, I'm writing everywhere, 1, 0, 0, 1. So immediately we have sort of a weird case here where, you know, obviously this is binary, so each digit can only be 0 or 1, and we're adding 2 ones. So what do? Well, just like in decimal, if you add 2 digits and you get a value greater than 10, you have to carry. So when you have 2 ones, the result that you drop below that is a 0, and then you carry a 1. So here now we have 1 plus 0 plus 0, so that's just 1, that's just 1, and that's just 1. And we can read this out as 8 plus 4, which is 12, plus 2, which is 14, and obviously that is correct for 9 plus 5. Let's look at a bit of a different case where we end up having 3 ones. I guess I'll just do 9 again. No, I have to do that. Okay. So in this case, we have the same sort of double 1 there. So we drop a 0 down there, carry the 1, but now we have 3 ones. And this, you've probably figured out, you just put a 1 down there and then carry the 1 like that. And oh, wow, we actually end up getting the same result. So what is this? This is 3 plus 8 plus 2, 10 plus 11. So that's 14. Oh, that's a good coincidence. Okay, so that's just signed integer addition. We're not going to do multiplication or anything. I honestly don't know how that works, but you're never going to have to do any of this by hand anyways. Okay, so now that everyone is hopefully on the same page of just like how to represent basic numbers as binary, let's look at signed values, so negative values. Now, for these examples here, you can see I was just using 4 bits, which isn't really like ever a type. Everything is in increments of bytes. So you have 1 byte, which is like a char in C, 2, which is a short, 4, which is an int, and 8, which is a long. But for some of these examples, I'll just do like 4 bits just because it keeps it simple. Hopefully that's not too confusing. But for signed numbers, it is actually very important to draw all the bits out. So I think I'll do it with just 8-bit numbers here. So with, I think first I will compare signed integers to unsigned ones, and then we will actually work through a signed example where we have like -5 plus 9. So with signed, the pattern, like the ith bit in the sequence counting from the right, represents the value 2 to the I. So like if I have 4 spaces here, this will be 2 to the 0, which is 1, 2 to the 1, 2 to the 2, 2 to the 3, and so on. And this goes all the way up until, or sorry, this is unsigned. Everything I've said so far is true for signed as well, but this next thing isn't. So all the way up until you have, you know, like the last bit of your number, I'll just call that 2 to the n-1 if you have an n-bit number. For unsigned values, all of these represent exactly these numbers. So if I had a 1 in this position and a 0 everywhere else, the value of this unsigned would be 2 to the n-1, because I have 1 times that plus 0 times everything else. But on the other hand, if I were to make this signed, the last bit is special. Last meaning furthest left, the most significant bit is what it's called. So the whole 2 to the I rule still applies for everything else. But in this case, we have sort of a special one, and I'll call this S. It's called the Sine Bit. And then we would have 2 to the n-2, ... and then 2 to the 2, 2 to the 1, 2 to the 0, and everything in between. Now this special bit is 0 if the value contained in the signed integer is positive, and 1 if it's negative. And that sounds simple, but it's actually a bit more complicated to store negative values than you'd think. So let's just take an example here of the value 6. So we have just 1, 1, 0 down there, 0 everywhere else in there. And then because this is positive, the signed bit would be 0. Now, obviously you can see 2 to the 2 is 4, plus 2 is 1, that's equal to 6. But now what if we want to store -6? Well, you're probably tempted to say, just get rid of that 0 and make it a 1, because that's the signed bit. So a 1 means it's negative. And for mathematical reasons that I don't understand, this isn't how it works. The reason it doesn't work like this is because if this was the way we stored negative numbers, where the only distinction between signed and unsigned was that 1 bit in the signed bit position, it basically means that you would have to implement separate operations for unsigned and signed integers and like the combinations of the two. A very simple one I can think of is that if you are comparing 2 numbers, let's take these, for example, where we have 2 to the n-1. Let's just call that, I don't know, 128, just to give it a real value. And this one, again, this is not how you actually store it, but assume this is how you store it. We would call this -6. 6 and then the 1 in the signed bit. If you're comparing these two, this one actually seems to be larger, because if you just go by looking at the most significant bit, okay, both of these have a 1 in the most significant bit. The rest of this is 0, but the rest of this has some stuff. So this -6 must be greater than 128. So that's an easy example of like where you would need 2 different types of operations. And it comes in play in addition and multiplication and everything else as well. And so the way that we avoid this is with a system called 2's complement. 2's complement. And this is sort of an extension of the way that unsigned values are stored, in that a lot of the properties are exactly the same. Like if you're storing positive values, it works exactly the same way, and you can count it exactly the same way as if it was an unsigned variable. But once you get into the negative variables and you have a 1 in that sign bit, everything else gets a bit weird. So for example, let's say I want to actually store -6, 2's complement of -6. So how would I do this? Well, I think I'll just show you and then I'll explain. So the trick for finding out the 2's complement of a variable is you take the absolute value of that. So absolute value of -6, which is 6. You do a bitwise not, which I'll explain the bitwise stuff later if you haven't seen it. And then you add 1. And the way I remember this is I just say in my head, flip the bits and add 1. And so what we get here is just take the bit pattern of the absolute value of -6. So 6, which is 0, 1, 1, 0. Flip that. So just flip all the bits and then add 1. So that's what 9 plus 1 becomes 10. So that becomes 1, 0, 1, 0. And you can notice, obviously this is a dumb example because it's just a 4-bit number, which doesn't really exist, but we do have a 1 in the sign bit now to represent that this is negative. But the rest of it, you can't really intuitively tell that that's 6, right? Like this just looks like 10 or like -2, basically, which is kind of weird. But there is actually a pattern to like why this happens, and it has to do with addition. And as I said, like everything else as well, but I don't know how to do like integer multiplication, bitwise stuff. So we're just going to look at addition. And the basic principle is that the 2's complement of a value in binary is such that when you add it to the non-2's complement, so the binary representation of the negation of a value plus that value equals 2 to the something. That's the pattern. So let's take another example here because I just said that and it didn't really make any sense. So let's define just some constants here. So n is the number of bits. And again, this will be some power of 2, some also multiple of 8. So I'm just defining constants here so I can write out a formula that actually makes sense. So the negation, so we have n, which is the number of bits, then we have x, which is just some number. It can be any number, assuming it's like within the valid range of the number of bits that we have. So the -x plus I need to define one last constant, which is b. So b is the bit pattern of -x. So in this case, like -6, that would be 1, 0, 1, 0 for the 4-bit value there. And the principle here is that x plus I don't know how to write this because there's not really an operator for it. So I'll just do this weird like homebrew thing. Or actually I'll just write unsigned. Equals 2 to the n. So what we have here is some number x, and then we do this flip the bits and add one trick to get the 2's complement representation of -x. And then we don't do any conversion on those bits. We store that -x in b. We don't do any conversion. We just tell the computer to interpret it as an unsigned value. So in this case, even though we know this is -6 because it's signed, the computer would say, okay, that's 10. And then what happens is when you interpret b the bit pattern of the negation of x and add it to x, you get 2 to the number of bits. And we can see that here with 6 and -6. So we have 6 is obviously just 0, 1, 1, 0. And -6, as we're saying, is that. And if we add these together, we have, I should read this out. We have 0, 0, which is 0, 1, 1, which is 0, carry the 1, 1, 1 again, which is 0, carry the 1, 1, 1 again, which is 0, carry the 1. And we end up with a 1 right there. And that's exactly what we want, because we have 2 4-bit numbers. In this case, in is 4. And we ended up with 0, 1, 2, 3, 4, 2 to the 4. And again, I don't know enough about this to like tell you why this works or how it was derived. But the representing numbers, negative numbers in 2's complement just means that you can treat the computer can treat signed and unsigned values the same when it performs operations on them, and it'll end up with the correct result every time. It doesn't have to know anything about their signedness. And this is, again, like this is probably the least useful of what we're going to learn today, just because it's sort of weird and you just never really have to worry about it. But it is still useful to know, and I think interesting, because that's not really a problem that like I ever considered. Like, how do you represent a negative number on a computer, and like having to treat them differently? I just never thought about that till I learned this. Okay, so we have a bit more to do with integers. I think I'll just give you like a quick little like table, just to show you like the common denominations of sizes in various languages. So Java, I think there's Java and like C and C++, and then Python and JavaScript. Obviously, everything is just like one integer or one numeric type. So in Java, we have byte, which is 8. We have char, which is actually 16. I'll write U for unsigned. That's the only unsigned type in Java. Then we have short, which is 16. This is annoying. It won't scroll down far enough. There we go. Don't want to just be writing at the top of the page, or the bottom. Okay. So a char is an unsigned short in Java, basically. And that makes sense, right? Because a char is just used to represent character values, and a negative character value, like those just don't exist. Like if you look at ASCII or Unicode, they're all just positive numbers starting at 0. Then we have int, everyone's favorite, which is 32, and long, which is 64. So in Java, everything except for char is signed, which that can actually come in handy if you end up with some weird functionality happening that you don't expect. And I'll talk about what I mean by that after this. So C and C++ is a bit different because in Java, everything is standardized. It all runs on the JVM, so they have complete control over the size of everything. But C and C++, like technically it's up to the compiler designer to determine the sizes of various things. So I'll just show you like the most common ones that are basically standard. Just know that you shouldn't like rely on these for size calculations or anything. So you have char, and then the one that is actually guaranteed to be that size, all right after the slash, int8_t, which is included in like a million different header files. You can probably just include any one and you'll get that. That's going to be 8, unlike Java, where it's 16. And note that this is signed. Chars in C are signed. Yes? These are the number of bytes. Sorry, number of bits. Number of bits, yeah. Next, we have short, which is, you can probably guess by the name, 16 bits. And in C and C++, short is also like kind of like a modifier to an int, but that's like an antiquated keyword, so I just won't. There we have that. And then in order to get 64 bits, long, which is another antiquated word in C and C++, actually it's like so old that it comes from the days when a long integer was also 32 bits. So to get 64 bits, you need a long, or the most common one that you should really always use if you're actually concerned about size, just because it makes the guarantee, is int64_t. And now note that unlike in Java, where we do have char, which is 16 bits unsigned, in C and C++, all of these basic types are signed. And the reason for that is you can just throw the unsigned keyword in the front of any of these, and then they become unsigned. So I'll write this just to denote that any of those can be unsigned. So if you wanted like an unsigned 64-bit integer, you could write unsigned long, whatever, or you could use the better type _t, mark that as unsigned, or even better, you could just use uint64_t, which is another built-in type that is the same as this. That's just a bit of a C++ tangent, though. Okay, there was something else I was going to mention. Oh, yes. So far, all I've said is that unsigned values can store only positive, and signed values can store only negative. So you might be thinking like, okay, well then like, what's even the point of unsigned values? If signed values can store positive and negative, and they both take up the same amount of space, the same amount of bits, then why do I even need an unsigned? And the reason is that back to, if I scroll way up here, they do actually use bits differently. This last bit in particular, the Sine Bit, the most significant bit, the leftmost bit of a signed value is special, as I said, and it's not special in the unsigned case. And what this means is, let's look at a quick like practical example. I think I'll just do 8-bit, just so I can actually write it out. So if we have unsigned byte, or I'll do C++, unsigned char, the values can be in the range. It's unsigned, so no negatives. So it starts at 0, and then it's going to go to 2 to the I. Well, this in particular will go to 2 to the 8 because a char is 8 bits minus 1, which is equivalent to 0 to 255. So 2 to the 8 is 256, minus 1 gives you 255. But a signed char, just a regular one, because that final most significant bit is reserved for denoting whether or not the number is negative, it goes from negative 2 to the 7 minus, I should write this 2 to the 8 minus 1 to 2 to the 8 minus 1 minus 1, which will be minus 128 to 127. And the reason that we have like one additional negative value is because the sign bit sort of serves a double role, in that because it is the most significant bit, if the number happens to also be negative, that one means I'm negative, but also my most significant bit is set. But when you just have an unsigned value, if you set that most significant bit, then suddenly it becomes a signed value. So you can only set however many you have here to 1, and it'll stay positive, basically. Does that make sense? Yeah, sort of. Okay, cool. So that's just a bit of practical knowledge. And I used 8 bits there just because I'm lazy and I don't want to write out all the long constants. But if I did this for like 32-bit, you'd probably see some large numbers that you're familiar with. Like the max value of an unsigned char is like 4,200,000 something something something, and the int is like 237 something something something. So I encourage you to mess around with that, because if you do actually end up seeing those numbers, which you can, especially in C and C++, where you have direct control over the signedness of a variable. Say if you have an unsigned int and somehow it wraps all the way back around to being like 4 billion whatever, and you can debug that and see that that's the value. What that usually means is that, okay, I had an unsigned value of 0, and then I subtracted 1 from it, and it looped back around all the way to the max value. And just as a side note, that's called integer underflow, where you go below the minimum value and it wraps back around to the top. And the same way, there's integer overflow, where you're at the top, you add 1, and then suddenly you're back at the bottom. And that just happens because there simply aren't enough bits to store whatever value you're trying to store. Okay, so next we'll talk about the bitwise operations on integers, and this will go super quick because it's very, very similar to the logical operation. So we have single ampersand, single vertical bar or caret, and then squiggly tilde. So and let me choose some good values here. So and if both of the bits in the input, oh, and these are used, by the way, these are binary operators. So you would write A and B, A or B, A XOR B, and this last one is just unary. So you would write not A. So A and B, if it goes, it's called bitwise because it examines them bit by bit rather than logical, which just looks at the whole value. And if it's 0, it's false. If it's non-zero, it's true. This looks at each bit individually. So if both of them are 1 and 1, you get 1. Otherwise, you get 0. So you would end up with that. I'll use the same values here. If either one of them in the input is 1, it's all 1 in the output. XOR is very interesting in that they have to be different. One has to be 1, the other has to be 0. Otherwise, it's 0. So in this case, they're both 1, so it's 0. But here we get 1. And same thing for that. And not A, I sort of already showed you in the trick, flip the bits and add 1. This is the flip the bits part. Just like that. And all of these are useful for various things. I don't think, I might come back to that if we have time, but I really want to get to floating point because that's the interesting part. Oh, and there are actually, yeah, I'll just mention this. There are a couple more unary operators. I keep scrolling down way too far. The bit shift operators. So you have right shift and left shift. I say these are unary. They're not at all unary. They're definitely binary, but they operate on one variable and they shift all the bits by some number that you give it. So I'll just do 1. So if I take my 5 from earlier and shift all of the bits right by 1, basically that just means I chop off the rightmost bit, and then whatever's at the front, I just slap a 0 in front of it. So this would become 0, 1, 0, because that 1 got chopped off, and then everything else before it. And same for right, you just shift everything to the right by adding a 0 in the left, or the least significant slot. So 0, 1, 0, 1 becomes 0, 1, 0, 1, 0. And this has the effect with integers, right shift multiplies by 2, and left shift does integer division by 2. And this is just sort of an artifact of the way binary numbers are stored, because the index of the bit like determines that bit's value. And so when you shift everything right by 1, where this one was previously 2 to the 0, it's now 2 to the 1. So everything that you have is multiplied by 2. And in this case, it's integer division by 2 because you just shift everything, you decrease it by a power of 2. And those aren't super useful, but they used to be used very commonly in old games where division was super slow. It was like very costly. So if they needed to divide by 2 or something that was approximately 2, they would just right shift by 1. And this is, I'll mention that later. But yeah, usually that's not used now. It is still very helpful though. And again, at the end, I'll come back to this and give you like an example of how I have used all of these operations before. But now let's get to floating point. So you're probably familiar with the two types of these. Unlike integers, there aren't a ton. I guess there aren't a ton in ints, but there are a ton of different sizes. For floating point, I'll just write it FP. We just have float and double. Those are like the standards. So float being 32 bits and double being 64. There are some weird formats. I think there's like an 80-bit double or something, and there's like a 128, 256, but those are like weird extensions. The ones that all languages support are 32-bit floats and 64-bit doubles. And these, they require a bit of thinking about like how we should store them. And I think the best way to start is like by considering the scope of the problem. So basically now we have a way of storing integers, but we need a way to store fractional values, so part of a whole number. But the problem is between 0 and 1, there are infinitely many fractional values. Between 0 and any other infinitely small fractional values, there are further infinite fractional values. And so like clearly there is just no way to store an infinite number of constants in a finite amount of bits. And that's just sort of a limitation you have to live with. It's like never actually really a problem though. I think, I mean, obviously these sort of extensions do exist for 256-bit doubles and stuff. That's mostly for like probably space-related scientific applications where like the numbers are just insanely massive. But for everything I've ever used, even float is good enough. And because float is half the size of double, it's hardware accelerated, it's preferable to double usually. But yeah, so these, they sort of give the illusion of storing an infinite range of values, but clearly they can't. And they store different ranges of values. We're not going to look at the exact ranges because they're sort of weird. But just know that double, because it's bigger, it has a bigger range of values, and it's also more accurate. But okay, so we've like gotten rid of the initial problem, which is okay, I want to store an infinite number of things. The way we got rid of that problem is just giving up, saying, okay, I can't do that, I give up. And that's fine. But now our next problem is, okay, how do I even store a finite number of values? And very early implementations of not floating point values, but of fractional values, I guess, of real number values, was called, confusingly, also FP, but it was fixed point. And this is basically exactly what it sounds like. You would have some number of bits, say 32, where I would have 16 bits and then like an implicit dot, the period, and then the remaining 16 bits would be the fractional part. So here you have the whole number, and here you have the fraction. But the problem with this is that it can't store that many values, it turns out, even in 32 bits, because if we sort of think about these as integers for a second, we know that 16 bits can only store up to 2 to the 16 minus 1, which is like, if it's unsigned, which is 65,000, and same here. So it's still a pretty, it's like very, very limited. And the further problem is granularity. Like, where do I put the point? Does the programmer get to decide to put the point, where to put it? But also, like, if they decide to put it somewhere else and say maybe this is only 14 bits, and then they have the period, and then they have the remaining 18, like, okay, they can store smaller fractional parts, but they lost a whole lot of values on the whole part. And so fixed point, while it was popular early on just because it's much easier to implement and like works intuitively, hasn't been used, I don't know, since probably the early 80s. But I think it is still useful to look at this and understand how it stores values, because it turns out it's like the way they store fractional values is still sort of similar to how we do it now in floating point. And again, this is something that you just wouldn't really think of. Like if you say, when I say, okay, you have 16 bits and then a point, and then the fraction goes in the remaining 16 bits. You say, okay, I know what a fraction is. Yeah, it's the thing after the dot. But how do you store that in binary? It's a bit weird, right? Like in decimal, we can just do 1.05. And say, okay, I have one whole value and then 5/100ths of a whole value. But you only have ones and zeros in binary. And the way it works is you basically just have to change how you look at it in decimal, and it works basically the same way in binary, just with a change of base. So here's the 10 to the zeros place. Here's the 10 to the -1, or tenths, 1/10. And here we have 10 to the -2. In binary, if we wanted to store this value, I'll write it down here, we would still have 1, because we have 2 to the 0. And then we have our fixed point there. And then we'd have 2 to the -1, 2 to the -2, 2 to the -3, and so on. And the problem here is we have 5/100ths. And so we need to convert that into binary. And I think this example, like I've shown how this is possible. So in the interest of time, because I want to get through this, I won't actually show this. But it is useful to think about it this way, where each position after the point is like half of the previous value. So this would be 1/2, this would be 1/4. And then to get the whole value after the point, you just sum together all of those fractional parts. Okay. So let's see. I'm looking for things that I can skip. So I guess I'll just go straight into it. Well, I did sort of mention that fixed point was used because it's easy to implement, it works intuitively, but it's very restricted. And the only way to really represent a larger range of values is with a floating point. And what that means is I have just 32 bits, and the point representing the fractional value could be here, it could be somewhere down here, whatever. But this, like, just thinking about it abstractly, that basically means that you need to, within the number itself, store some like metadata about where that point is located for that particular value. And it turns out that a very natural way to represent this, that like achieves what I just mentioned abstractly, where like the point is in different places, we also already do in base 10, which is scientific notation. So in scientific notation, you have some whole number, a point, and then, you know, your fractional part, but you always have a whole number up front. And then that's going to be multiplied by 10 to some value, some n. And obviously, if you make n negative, you get a fractional part. So this can store whole numbers, like bigger and smaller numbers. And we just sort of convert this to binary. We just sort of change the base. But in general, the formula for like a number x, just in base 10, written in scientific notation, is going to be the sine, which I've sort of separated out as a separate value, which is just 1 or -1, because it's convenient for how it's stored in binary, times s, which is like this part, times the base that you're working in, raised to e. That's a bad, because e is a constant, raised to n, which is just some number, basically. So obviously, in regular scientific notation, the sign is 1. The sign is always going to be -1 or 1. The s is whatever value comes first. B will be 10, and then n will be whatever n we have over here. But in binary, all we have to do is replace b with 2, and we've got it. And this is, it's not the way that all floating point systems represent them. I'll just rewrite it for clarity. Times 2 to the n. But the Ieee-754 Standard, which is a really like weird long name, but you will see that over and over again. That's the standard that like everything uses now. And the base is always 2 in that, and that's the one we'll be looking at. So essentially what we have here is we have 4 components, or no, we have 4 components up here, but because we've simplified it and the base is always 2, we have 3 things that we need to store in our numbers. We have the sign, which is just -1 or 1, and just like unsigned values, we can store that in a single bit. Then we have s, which is some integer part, and then we have in, which is the exponent. And the way these are stored, they're stored in this order. You will have a single bit, which is the sign bit, where 0 means positive and 1 means negative, just the same. Then you will have some number of bits representing the exponent. And then the rest of your bits are something called a mantissa. And I have no idea where that word comes from, but basically that's just the fractional part. So I'll abbreviate these. So the formula here to convert this to a base 10 value that we can read would be s times, well, actually, I'll talk about that. 1 plus m times 2 to the e, because the base is always 2. But the m, why do I add 1 to the m? The reason is that in scientific notation, there is always like this is not scientific notation, right? You have to have some non-zero value before the point. That's just how it works. And in binary, there is only one non-zero value that you can have before the point, which is 1. So implicitly, there is always a 1 added to this mantissa. And that just gives you like an extra bit of freedom, basically, for a smaller value that you can store, because that 1's always going to be there. So you kind of just factor it out. Okay, and I guess I'll just give you the values for 32-bit and 64-bit. So float and double. As I said, the sign bit is always 1. E, the exponent, you get 8 bits for float, 11 for double. Mantissa is 23 for float and 52, I think, for double, if I did the math right. Looks right. But that's not super important. Okay, now there is one last interesting thing about floating point values, which is the way that the exponent is stored. And it's not, you would think that it would just be the like 2's complement thing that we learned earlier. That's how you store negative integers. But for whatever reason, again, I don't know why, I can only assume that it's to simplify computation, basically, so that the CPU doesn't have to worry about 2's complement in addition to all this other stuff. The exponent is instead biased by a value of -127 for a float, because a signed 8-bit value can go from -128 to +127. And so basically what that means is if you have an exponent of 0, then in the actual calculation, how this number is interpreted, that becomes -127. And similarly, if you have 127, that becomes 0. So our final formula then for actual, like the actual value, is the sign bit s times 1 plus the mantissa times 2 to the e minus 127, that bias there. And then the mantissa, I already explained that. That's the fractional part is just stored basically how it is in base 10, where each successive bit is 1/2 the value of the previous. So let's do a little example here, just to make some of this concrete. Let's say I want to store the value like 1.625. I think that'll end up working. So this is, I'll just write out the 32-bit version. So we have 0 in the sign bit because it is non-negative. Then the exponent that we're going to have is just going to be 1. because this is a pretty small number. And remember, the 1 is going to be added to the Mantissa implicitly. But in order to get an exponent of 1, we have to remember that we are subtracting 127 from it. How do I want to write all of this out? I'll just store the value. I'll just write the decimal value because I don't, well, I could, I'll just do that. Okay, 128 is, this is 8 bits. So that's going to be 1. Okay. I decided to do it that way because I am going to write out the Mantissa as well. So this is the hard part, the 0.625. But all we have to do is start from remembering that the Mantissa starts at 1 over 2 to the minus 1, and then 1 over 2 to the minus 2, so on and so forth. We just have to start from this value, and if we can subtract it from our fractional part here without going negative, then we do. So we have 0.625 minus 0.5. So we get 0.125. And we could subtract it. So we put a 1 there, which represents 0.5. Next, we have 1 over 4, which is 0.25. We can't subtract that. That's too big. So we put a 0 there. Next, we have 1 over to the negative. Oh, wait. Yeah. We have, I shouldn't, sorry. That's just 2 to the negative 1, 2 to the negative 2, and 2 to the negative 3. 1 over 8, which is 0.125, convenient. So that's a 1, and then we can subtract 0.125, we get 0, so we're done. So the rest of these are just 0. And we can actually check this with a cool tool that I found online. Let me bring it up here. It is a pretty old website. Let me just drag this over here so we can see R, the binary number that we came up with, and we can put it in here. And I'll like fully expand this once it's typed out and see what we get. So this is just 32 bits. So we have 0 in the Sine bit, which is good. Then we just have a 1 in this bit. And then we sort of have to do some counting here by hand. So the exponent is 1, 2, 3, 4, 5, 6, 7, 8 bits. And then after that, we have 1, 0, 1. Did that? It may have done something weird, but let's see what we get. And if I hit enter, I think it added 2 zeros. Maybe just 1. Or maybe I didn't count right. 1. Let me reload. I don't know what I did. Okay, 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 0, 1. Oh, I forgot the. Dang. Well, that sucks. This was supposed to be a cool demonstration. Let's see. It does actually show us the representation up here. Why is the Sine Bit 1? Two to the 0. Oh, you're right. You're right. Okay, so that should just be 0. Thank you. So these 4 are 0. The next 4 are 0. And then we have 1, 0, 1. Okay. I don't know what I'm doing clearly. Yeah, there's something weird going on here. I think. Okay, that worked. So yeah, I just did some conversion weird. I think it was that 2 to the 1 thing here. But yeah, anyways, that was a failure. Okay, so one last thing I'll mention, just to sort of follow the structure of how I talked about integers, all the bitwise operations, those don't exist for floating point. They just, it doesn't really make sense because of the way these things are stored. There's no real practical reason to like flip all the bits or and them with anything or shift them, because in integers, those actually do serve a practical purpose, like shifting, just multiplies by 2. Shifting left multiplies by 2, shifting right divides by 2. But as a last side note, something interesting for you to check out is this very famous algorithm. Well, it's now known as FISR, fast inverse square root. I know it as Q_R square root. That's the name of the function where it first showed up. And this is from Quake 3's software renderer, which just means the part of the code that drew graphics if the computer it was running on didn't have a graphics processor. Because nowadays, every computer has some type of graphics thing. Either it's a dedicated GPU or something built into the CPU, like integrated graphics. But back in these days, that wasn't a guarantee. And so it turns out that a very, very common operation in computer graphics is normalizing a vector, a 3D vector. So vector is just X, Y, Z. And then to normalize that, meaning you want to get it pointing in the same direction, but just of length 1 for lighting calculations, you end up needing to divide by the magnitude of that vector. You divide all the components by x squared plus y squared plus z squared. And then so on and so forth. And so that's where the r square root comes from, is this algorithm would return, I guess I'll just write the little signature, float Q_r square root of a float x. It will just return 1 over square root of x. But it did this insanely fast, and it was not perfectly accurate, but the approximation that they were able to achieve is pretty astonishing. Nowadays, it's completely irrelevant because all of our CPUs just have, all the rendering is done on the GPU anyways, but all of our CPUs have just square root instructions and trig instructions and stuff that are way faster than this. But if you want, the reason I brought this up is in order to achieve this performance, they did something technically undefined in C, which is they took the bits of this floating point x that you've given them, and they just sort of jammed them into an integer value. They didn't do any casting or anything. They just copied the bits into an integer and then shifted it. They right shifted by 1, which if you remember for an integer is equivalent to dividing by 2. And it turns out for a float that gives a very rough approximation of dividing by 2, because if you shift this left, you end up with an extra 0 on the left side of the exponent and 1 less 0 on the right side. So you do lose some accuracy in Mantissa, but it sort of gives an extremely rough approximation for 1/2 of the exponent, which is equivalent to the square root. And then there's this crazy magic constant involved, and they do some other math, some calculus with Newton's method. It's a very clever algorithm. If you're interested, there's this great video on YouTube. It's just called this fast inverse square root. And the guy explains the whole thing from start to finish, including how it interacts with the Ieee-754 floating point standard, and how they made it work and everything. But yeah, so that's all I had planned for today. If you want, you can stick around a bit for just a couple minutes, and I can talk about how I've used bitwise operations on integers, how those things are actually valuable still, even though they seem very irrelevant. But yeah, you are free to go. Thanks for coming. And next week, we will look at printf, which is a pretty cool function. And if we have time, I'm not sure if that'll take the whole hour, if we have time, we'll start also looking at regular expressions, which are a very complicated topic, but very useful. And those I definitely have some practical examples that I can show you of just how I use these to like manipulate some arbitrary data that I need to change the format of. But yeah, thanks. Yes.